In this video, we're doing a lot of things that we did in the last couple of videos, but we're doing it for a function that involves a trigonometric function, and it's on a closed bounded interval, so that's a little different too. We've got this function. We're told that we're on an interval from 0 to 4 pi, and we want to know where the function's increasing and where the function's decreasing. We want to know where the graph is concave upward or concave downward. We want to determine the relative extrema on that interval, and we can use the first derivative test or the second derivative test. I like to use both to confirm. Then we'll find any points of inflection, and we'll find the absolute extrema of this function on this interval using the extreme value theorem, and then we'll graph the function. So first we need to think about the domain. Actually, it's already given to us. It's 0 to 4 pi inclusive, and this function is well defined on the interval from 0 to 4 pi. So the domain is settled. They told us that this was the interval, and we see that there are no asymptotes or issues with this. We don't have to worry about dividing by 0, taking even roots of negative numbers or logs of negative numbers or 0, so we're good there. The next thing we do, if we want to determine where the function is increasing or decreasing, is we compute the first derivative, and we find the critical points using that first derivative. So we want the critical points of the function, but only on the interval from 0 to 4 pi. And we really don't even need 0 and 4 pi. Could probably just do the open interval because we're going to determine things about the absolute extrema later using the endpoints, but either way is fine. So we'll find the critical points. And remember how we do that. To find the critical points, you compute the derivative. You set the derivative equal to 0 and solve for x. So we're looking for those points where that slope is 0. So that might be a hill or a valley. It might be a max or a min. And then we also want to consider any x values for which the derivative is undefined. So any x in the interval that they gave us, 0 to 4 pi, for which y prime is undefined. Okay, the derivative of cosine of x is negative sine of x. The derivative of negative x is negative 1. That derivative is well defined for all numbers, so we don't have to worry about this first part, or the second part, excuse me. Now we just need to set that equal to 0 and solve. So I've got negative sine of x minus 1 equals 0. Well, that means that negative sine of x equals 1. Or we can multiply both sides by negative 1, and we get sine of x equals negative 1. Now you can graph this, you can look at the unit circle, and you can figure out where the sine of x is negative 1. I prefer to just look at my sine wave. We're on the interval from 0 to 4 pi. So we get 2 periods. There's 2 pi, and there's 4 pi. This is not to scale, those are both supposed to be 1. That's negative 1. Say, well, where are those x values where sine is negative 1? What are the x values there? Well, all the interesting things happen with our sine and cosine graphs at 1/4 of the period. So that was pi over 2, we get 1. At pi, we get back to 0. And at 3 pi over 2, we get negative 1. So that's one x value. And the pattern repeats over here. So that's pi over 2. 3 pi over 2. This next one's going to be 5 pi over 2, and then 7 pi over 2. So the two x values where the derivative is 0 are x equals 3 pi over 2 and x equals 7 pi over 2. So those are our critical points. Now we're trying to determine the intervals where the function is increasing or decreasing. In order to do that, we need to look at the SIGN sign of y prime on the intervals defined by these 2 points and then the endpoints of our interval. So we're going to draw a number line. We're going to make a sign chart again, but this time the sign chart doesn't include all real numbers. It only includes the numbers between 0 and 4 pi. So we start at 0, we end at 4 pi, and somewhere in here we've got a 3 pi over 2, and somewhere over here we've got a 7 pi over 2. And we want to know what is the SIGN sign of negative 1 times sine of x plus 1. That's what happens when I factor out that negative. Well, I can graph this function, and then I can look at the graph, and that will tell me when this function is positive or negative. Actually, maybe I want that distributed again, sorry. So we know sine of x looks like this, and the period is -1 to 1. If I multiply that sine function by a -1, that just flips it upside down. So instead of going up first and then down, it goes down first and then up, because it takes all these y values, which were positive, and it multiplies them by -1, making them negative. And it takes all these negative y values, and it multiplies them by -1, it makes it positive. It makes them positive. So this is y equals negative sine of x. There's like a hole, there's a hole punch there, so I can't really write the x, but I think you get the idea. Then we take that graph, this red graph, and we move it down 1 unit to get the graph of y prime. So y prime, it's not that red graph, it's this graph. Take the red graph and move it down 1 unit. And we actually want it on the interval from 0 to 4 pi. So this is 2 pi. This is not to scale, but that's 4 pi. Okay, that's interesting. The blue graph is our derivative on the interval from 0 to 3 pi over 2. So that's the interval from here to here. Just focus on the blue graph. Don't be distracted by all the other graphs. Notice all those y values are below the x-axis. So that means y prime is always negative there. What happens on the interval from 3 pi over 2 to 7 pi over 2? That's 7 pi over 2 where it crosses, or it's 0 again. All the y values are negative there as well, because they're all below that x-axis. And then they're negative over there. So it looks like we don't have that's really odd. We don't have any extrema. Did I make a mistake? The interval from 0 to 4 pi. That does not make sense to me. Add 1 to the other side, divide by -1. Okay. All right, I'll keep making the video. We'll see. We'll see. I might have to toss this. Okay, so where is the function decreasing? The function is decreasing on 0 to 3 pi over 2, and 3 pi over 2 to 7 pi over 2, and 7 pi over 2 to 4 pi. It's never increasing. Okay. Second question is, where is the graph concave upward versus concave downward? In order to figure that out, we need to take the second derivative. The first derivative is negative sine of x minus 1. The second derivative is the derivative of this. Derivative of sine is cosine. So we've got negative cosine of x. Now we're on the same interval. We're on the interval from 0 to 4 pi. The question is, where is this graph concave upward and where is it concave downward? Or initially, where is the second derivative 0? The second derivative is well defined for all x. but there's a chance it could be 0. Well, it's 0 whenever cosine is 0. So let's look at the cosine graph on the interval from 0 to 4 pi. So we start at the, well, cosine starts at a max, but we're going to multiply it by -1. So negative cosine starts at a min, then it's 0, then it goes up to its max, and then it's back to 0, and then to -1. And then back to 0, then to a max, then back to 0, then to -1. So this is cosine, or negative cosine of x. Okay. So I can see right now, just looking at the graph, where the second derivative is 0. The second derivative is 0 wherever the y values on the graph of this function are 0. Well, they're 0 there, 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 and there. That's at pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2. And we're on the interval from 0 to 4 pi, so I guess I don't need those arrows. I need that, 0 to 4 pi. So there's pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2. And we want to know, where is the second derivative positive versus negative? Well, let's look at where it's negative first. Second derivative is negative whenever this graph is below the x-axis. So it's negative there, and there, and there. Well, that's the interval from 0 to pi over 2, then 3 pi over 2 to 5 pi over 2, and then 7 pi over 2 to 4 pi. And then it's positive in between, so it's positive on those guys. So this is telling us the graph is second derivative. So we're interpreting this as concavity, not slope. Over here, the function is decreasing. First derivative was negative, that meant the function was decreasing on all of those intervals. This tells us the function is concave down on this interval. When the second derivative is negative, it's concave down. When the second derivative is positive, the graph is concave upward. Then it's concave downward, concave upward, concave downward. You're saying to yourself, how are we going to put all of that together with all of that? You'll see. We'll see very shortly. Okay. And we've got increasing and decreasing. Turns out it's always decreasing, so there are no relative extrema according to the first derivative test. Where is the graph concave downward versus concave upward? We've got that right here. Let's answer the question. The graph is concave downward on the interval from 0 to pi over 2, and the interval from 3 pi over 2 to 5 pi over 2, and the interval from 7 pi over 2 to 4 pi. And the graph is concave upward on these intervals, pi over 2 to 3 pi over 2, and 5 pi over 2 to 7 pi over 2. Okay. Now I don't have any critical points. Well, I did have critical points. Ooh, actually, we had 2 critical points at 3 pi over 2 and 7 pi over 2. Well, at 3 pi over 2, the second derivative was 0. And at 7 pi over 2, the second derivative was also 0. Since the second derivative is 0 and the first derivative is 0, well, the second derivative test is inconclusive. It doesn't tell us anything. So, all right, can't do much there. Can't do anything for a relative extrema. Now we want to know what are the points of inflection. So those are the points on this interval where the graph changes from concave upward to concave downward. Looks like we've got a lot of them. I've got 1, 2, 3, 4 points of inflection. So we just need to find the y values on the graph for each of these x values. And our graph is cosine of x minus x. So I've got x equals pi over 2, x equals 3 pi over 2, x equals 5 pi over 2, and x equals 7 pi over 2. And those are all points of inflection. Y is cosine of pi over 2 minus pi over 2. Y is cosine of 3 pi over 2 minus 3 pi over 2. Here y is cosine of 5 pi over 2. You get the idea. Now, if you remember properties of cosine, you might already be thinking, that's interesting. If not, that's okay, I'll remind you. This is pi over 2. That is 3 pi over 2. This is y equals cosine of x. So the function cosine of x is 0 at all the odd multiples of pi over 2. Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. So all of these are 0. You're saying to yourself, what? I know, me too. So I've got this. So our points of inflection are these, pi over 2 and negative pi over 2, 3 pi over 2 and negative 3 pi over 2, 5 pi over 2 and negative 5 pi over 2, and 7 pi over 2 and negative 7 pi over 2. The y value and the x value are opposites of each other. So these are all points on the graph y equals negative x, because all of those are gone. Okay. And we want absolute extrema now. Well, according to this, we don't have any relative extrema. The function goes from decreasing to decreasing at those points. But normally, if I was using the extreme value theorem, I would evaluate my function at the critical points and see what the y values are. Actually, 3 pi over 2 and 7 pi over 2, we've already done that. They're right here. So we would evaluate those functions, find the y values. Now we also have to find, when we're finding absolute extrema, we have to find the y values at the end points as well, as 0 and 4 pi. So when x is 0, y is cosine of 0 minus 0. That's just 1. And when x is 4 pi, y is cosine of 4 pi minus 4 pi. That's 1 minus 4 pi. Okay, and I think with this one it's helpful to get some numerical approximations of everything. So this is pi over 2 is about 1.57. Actually, we could probably just draw our graph with multiples of pi over 2 on it. Let's do that. So I've got 0, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi, and 7 pi over 2, and 4 pi. When x is 0, y is 1. So this is about 1.6, so I'll just make my 1 right there. And when x is negative pi over 2, or excuse me, when x is pi over 2, y is the same number but negative. And when x is 3 pi over 2, y is the same number but negative. Has the same magnitude. So I'm just graphing all of these. There's that first point of inflection, there's our second one. Okay. At 5 pi over 2, y is negative 5 pi over 2. At 7 pi over 2, y is negative 7 pi over 2. And then at 4 pi, y is 1 minus 4 pi, which is about negative 11. Let's subtract 1 from that. So this is negative 12.6 approximately. It's right here. And let's do negative 7 pi over 2 as well. So this is about negative 10.99. So 1 minus 4 pi. It's negative 11.6, so it's like here, approximately. Whoops, just there, sorry. I'll just say not to scale. There we go. Okay, so those are points on our graph, and we wanted to find absolute extrema. We wanted to find points of inflection. There were 4 of them. We wanted to find relative extrema. Apparently there are none. We wanted to determine the intervals where the graph is concave upward and concave downward, increasing and decreasing, and then put all of that together to graph a function. So according to this, it looks like we've got a slope of 0 at 3 pi over 2 and 7 pi over 2. But the graph is decreasing the whole time. So let me put this together on a little chart. We're on the interval from 0 to 4 pi. And I've got multiples of, or odd multiples of pi over 2 right here. Oops, I guess I should have shouldn't have made that so long. There we go. Okay. So according to this, our function's decreasing, then we have a 0 slope, then it's decreasing, then we have a 0 slope, and then it's decreasing again. So it's decreasing on that first interval, then decreasing on this long interval, and then decreasing. And then over here, from our second derivative, from our sign chart for that, we got concave down, concave up, concave down, concave up, concave down. So I'm just going to write down, up, down, up, down. Okay, what on earth? That's what you're thinking, that's what I'm thinking. Whoops. Okay. So initially it starts decreasing and concave downward on this interval from 0 to pi over 2. So I think what we get is something that looks like this. It's decreasing and concave downward. Because remember, concave downward looks like this. If it's decreasing, it's just that side. Now over here it's decreasing the whole time. And we also are supposed to have actually a 0 slope at pi over 2. Ooh. Okay, so I'm going to have to change that a little bit. It's decreasing and it's concave downward, and then it switches to being concave upward there. But it's still decreasing. Oh, actually it's not at pi over 2, it's 3 pi over 2 where it has the flat spot. That's good. So it goes from decreasing and concave downward to decreasing and concave upward, and then it has a flat spot, 0 slope right here, Then here we've got it's decreasing in concave downward. Then it's decreasing in concave upward. Zero slope, decreasing in concave downward. Now, I didn't make my graph very smooth, but I think you do get the idea. See how it's a little different. At first I thought I was wrong, but I guess all my calculations were right. Just gotta trust the calculus, I guess. So the function is decreasing concave downward, decreasing in concave up, and then here is the point where we had a zero slope. We got a horizontal tangent line there. Decreasing in concave downward, decreasing in concave upward, zero slope over here, and then it's decreasing again. Now these points of inflection are where it's changing from concave upward to concave downward. This one, we don't have a zero slope, but we've got a vertical tangent line there. You can kind of see it. If I had done a better job drawing my picture, if you graph this using Desmos.com or some other graphing software, you'll see that the tangent line is vertical at these 2 points, and the tangent line is horizontal here. So it's going concave downward, concave upward, concave downward, concave upward, concave downward, and it's decreasing the whole time. So we don't have any relative mins or maxes because it was decreasing, and then it was decreasing, and then it continued decreasing. So we've got no relative extrema. So that is how you handle all of this for a trig function on a closed interval. It's a tough question, and I know initially I didn't really trust myself right here, but I should have. The calculations were right, just wasn't what I expected. Maybe that will happen to you too. Now you know what to expect.